And finally, we will conclude our discussion of regression by using linear regression to predict the expected damages that a car will have during its policy lifetime. And we're going to expand upon the code that we did in a previous lecture where we were using decision trees, random forest, and gradient boosting to predict the claim amount, which is the amount of expected damages that a car will have. So let's just get started. Now, one thing you need to do is add one more library now. This is the mass library, and that's going to allow us to do stepwise selection of variables. So let's bring all that data in, or load in the libraries. Okay, and now we will load in our data set. And if I were to look at data frame amount, let's do the head command. And you can see we've got all the variables, and now we have the claim amount here. So in other words, this guy didn't cost us anything because they didn't crash their car, but this person did crash their car and it cost $6,872 to repair it. Okay, now we're going to split the data into a training set and a test set. So let's do that. Whoops. Control C. And there we go. Now if I look at the dimensions, oh, I don't even need to do that. Let's just, what I would like to do is make sure that the average damages are about the same in both groups. So the average damages on the entire data set is $1,511. For the training set, it's $1,512, and for the test set, it's $1,507. So that's pretty close to one another. If there was a wild disparity here, we would probably want to, shuffle the deck again and do a different, try splitting it again. But they will typically be about the same. So we'll start again with our friend the decision tree, and we will build a decision tree to predict damages. And you can see the average damages is $1,513. But if you live in the country, you don't crash your car as much, it's much less damage. You come over here to the person who lives in the city. They have a blue-collar job, so they're always in the car. And over here, they're not married, so they drive more recklessly. This person is more likely to cost us $3,000 in damages. So this is our decision tree, and these are our predictive variables. The ones that the decision tree predicts are highly predictive of whether or not you're going to damages that we have to pay. And we're going to use this later on. Let's just predict the root mean squared error on the test data set. So when we do that, we can see that the, if we print that, it's $4,600. That's our expected error. The less the error, the better. Now let's do the random forest. And this might take some time, so while this is running, I'm going to pause the recorder so that we don't have this awkward silence. And we're back, and we have here the random forest predictive variables, and the random forest has succeeded in running. And now we will do the gradient boosting model. And that one should be a very quick one to run. And there it is, it's done. And now we will begin to do linear regression. Now, for this time, just to mix things up a little bit, I'm going to start with, well, first of all, as before, we're going to do a linear model with everybody, and then a linear model with nobody. So we're going to do those two. And now we are going to, we can just summarize. Let's just summarize the top guy. And that's got a 6.9% R squared, adjusted R squared. Now, incidentally, from the insurance industry, predicting damages is a nightmare. It's a very difficult thing. So having such a low R squared in insurance is not unusual. It's fact, it's expected. You will find that this R squared value will depend from, will vary from industry to industry. So this is about what you might expect in auto insurance. Here's the summarization of our model that used no variables. And now we will do a backwards selection. We will start with the upper, meaning we're going to start with everybody. We're going to go in a backwards direction, and we're going to say that the final model should have something between nobody and everybody. So let's watch this guy run. So he starts off with everybody. Let's there it is. So he starts off with everybody, and you're watching the AIC's value go down. And he keeps deleting variables until eventually it gets down here to the lowest possible. We throw out the Dunzel variables, Dunzel meaning you can throw out the variable and the model will not deteriorate. Let's just see how well the model performed. It used to be about 6.9. Let's see where we're at now. Now we are at 7.1%. So we did well. We got rid of variables and the model improved. Now let's predict the test variables, and then we will now predict the root mean squared error of this linear regression. Now we're also going to do what we did with the logistic regression. We're going to ask R, what is the decision tree? We're going to say, hey, listen, what variables did the decision tree think was important? Remember, our decision tree was the first model we built. And here we have all of the variables that the decision tree liked. And then we can say, well, we don't care about the importance. We just want to know the names. So by using the names command, it's just going to give us the names. And those are the important variables. And now we're going to, again, as we did before, paste this plus sign in between all of them. And if we do tree vars plus, we get a big giant string with a plus sign in between each one of them. And then we make a formula where we say the target amount, squiggle, equals all those pluses. And we have to say as a formula. So we're going to tell R that this is a formula that we're going to put into our regression. And if I type in F, there it is. That is the decision tree's variables put into a formula. And we can do a linear regression of the tree. And well, let's also make the lower bound again. So this is a linear regression using only the variables that the decision tree liked. And this is a linear regression using nothing. So we could do, let's summarize the tree, see how well that did. It's got an adjusted R squared of 5%. So it actually did worse than did using all of the variables. But like I said, there's no guarantee that any of these techniques will be the best. You try lots of them and you see which one's going to be the best. And here's our model using no variables. Now we're going to do a stepwise selection, and we're going to start with nothing. We're going to go in both directions. We're going to add and delete stuff, and we're going to say that the final answer should have something between no variables and all of the variables that the decision tree likes. So let's do that. And this shouldn't take very long. And there we go. So this is a smaller subset of the variables. And let's just see how well this guy did. It's got 5.6% adjusted R-squared. So the adjusted R-squared isn't anything to write home about, but you know, it's there. Now we're going to, what I would like to do is do a predictive, predict using the tree by itself. So in other words, we got this guy sitting out here anyway. Why don't we just see how well he did? And then we're going to do another one using the model that we created with stepwise regression, the linear regression tree model. So let's do both of those guys. And now let's ask R, hey, listen, we built 6 models here. We got a tree, we got a random forest, we've got a gradient boosting. We did a linear regression using backwards selection. We used linear regression using only variables that the tree liked, and then we used a linear regression using the tree variables, but then we did a stepwise selection. So let's see which one of these performed the best. And 4689, 4648, so that's pretty good. That's the best so far. 4631, that's even better. That's the lowest. 4637, this is a little bit worse. And then 50 and 51. So the two best are the gradient boosting and the linear regression. So as before, the difference between these two is not very big. So I would probably go with the linear regression using back substitution, because that one will be something we can explain to a regulator. A gradient boosting is a black box. It's not something that you don't know what's going on in there. And so sometimes it's okay to take and use a slightly inferior model in exchange for ease of explaining or understanding of it. So we will probably go with this guy right here. So anyways, this is linear regression to predict the amount or the damage amount.